3 to 8 seconds. Hi, good afternoon. Well, we have 19 students, maybe 17 students. Oh, 17. Can you hear? Yes, good. So today, we'll cover the second part lecture about the introduction to the algorithm. Yeah, so we'll cover about the how we conduct the complexity analysis of algorithms. Well, today we only have 24 viewers. Don't know why. We have 600 plus students. This attendance rate is very low. Never mind. But I have to say that this part is, you can think is very theoretical, but is something fundamental and important, because in the 2000 module or higher level, you not just trying to know, you don't need, it's not only you, we assume you know that, but you not only need to know how to implement the algorithm, you also need to know how to analyze them. Especially people working in higher level, and you having a good, you need to know how, whether your algorithm is good or bad, and how do you evaluate it is good or bad algorithm. How do you define good algorithm and how do you define bad algorithm? That's one thing. And another type of people need to know is they have the resource limitation. Yeah, especially those people maybe computer engineering student working in embedded system. You got the memory limitation, or sometimes you need to run your program in real time. So your algorithm, whether it can be run in real time or not, or under certain limitation, resource limitation, your algorithm need to do some complexity analysis. And of course, those people working in theory, they need to analyze the performance of their algorithm. They need to do this complexity analysis. Yeah, so we will cover this in this lecture, probably today and next, after recess week, in week 8 Monday. Yeah, we will cover the time. Today we will cover time and space complexity, and what is the best case, worst case, average case, or efficiency. And after that, maybe Monday, week 8 Monday, we will cover the asymptotic notation. How do we represent? After you analyze it, how do you represent your complexity? Yeah, so we will introduce a few notation, which you may heard about it is a big O notation, and big omega and big theta notation. And what is the difference between this asymptotic notation and what is asymptotic? Yeah, this will be covered in this section, this lecture. Maybe the details. You also, whatever I'm going to talk, you can easily find most of the content in our PDFR, in the PDFR notes. Yeah, so most of stuff will be here. You can take a look. Okay, put back my. Okay, still very low, only 35. Okay, never mind. So time and space complexity basically is trying to analyze the efficiency of an algorithm in two aspects, not surprising, in terms of time and space. Yeah. The time complexity means that the amount of times you use on the to running to execute to on an algorithm. Yeah, that is the amount of times. And then second factor we will consider is the space. Space complexity is the amount of memory. Typically, it's the memory we use by the algorithm. Yeah, that will related to your what you have learned earlier, the data structure. Because how much data structure, the linked list, stack, queue, tree, array you have created in your algorithm, it will affect the space complexity. Time complexity, one thing is like amount of times, but it should be independent to the processor you use, the computer you use. So how do we represent the times is an issue. How do we represent the amount of memory? Probably here we will focus on the time complexity only, but the space complexity, the representation, the analysis should be very similar to the time complexity. And time complexity, the analysis normally is harder than the space complexity. So what is the time how do we analyze the time complexity? Basically, it's trying to count the number of primitive operation in the algorithm. So that is the keyword is primitive. What is a primitive operation? For example, you declare a variable that is this integer x or double or character or array. This is one considered declaration is one type of a primitive operation. Another one, maybe you assign a number, that is another operation. And sometimes you maybe do this two in one line, but that still in the computer, how they process it actually is considered two operations. They need to declare. After they declare, they assign the number to the variable. So there are two steps actually. Then all kind of arithmetic operation, plus, minus, multiplication, division, modulus, they are considered primitive operation. Typical any programming language, any computer, definitely there's a arithmetic operation and logic operation. Because in the processor, there's they basically only can do arithmetic and logic. There's a unit called arithmetic logic unit, ALU. So this is the very basic operation what computer can do. So logic operation, equal, not equal, greater, lesser, and or not, all the Boolean algebra operation. All these operation, if you look at each operation individually, like declare the variable, do the assignment, and or doing any arithmetic or logic operation, the time they take is a constant time. Maybe some of them need to take a little bit longer. Some of them may be a little bit faster, depend on your processor. But generally speaking, all of them take constant time to perform. So, this operation, individual operation, basically not related to the problem size. That means my problem, my input have bigger input or smaller input. Each operation you declare a variable, you assign 1 to x, you do a simple summation, you do a simple subtraction, you do a simple multiplication between two numbers. The problem size changes, your input changes, it should not affect the operation time. In fact, 1 plus 1 compared to 1 million plus 1 million, to computer, actually, the time it takes is about the same. So changing the input does not affect the computational time on this primitive operation. So the thing will affect the computational times is in your algorithm there's some for loop, while loop, yeah, so-called the repetition structure, or you have some selection structure or control structure, if else statement, switch case, yeah, it will affect your computational times significantly, especially the for loop, while loop. And if else statement will change the result when you have different condition. Under different condition, you may have different complexity. Another one we will discuss, maybe hopefully can be covered today or maybe in week 8. That is more important one. It's a harder ones in the time complexity analysis. It's a recursive function. Yeah. So, and all of them the time complexity we're trying to represent in terms of its problem size. So problem size, yeah, we need to consider it's not just today this particular algorithm for this particular input. We're trying to analyze it as a general. So we use the problem size as a term, as a factor, or input argument for this time complexity function. Yeah. So my problem size, I mean when I n, my number of n or m or whatever increase, how does it affect my program? How does it affect my algorithm? For example, the repetition structure. Yeah, here we're trying to have a while loop to calculate the factorial. So first I assign j 1 to j. So this one, as I mentioned earlier, it is a constant time. You assign 1 to factorial. This variable, yeah, you take another constant time to do so. But C0 and C1, the different, generally speaking, should not have any big difference. And then in line 3, you're trying to check whether j is less than the n. Yeah, if j is less than n can be any number, can be from 1 to 1,000, 1 million. Yeah. Then that will decide how many iterations I need to run in line 4 and 5. So line 4 and 5, both of them again are constant time. It's a primitive operation. One is the multiplication and then assignment. Another one is addition, then j plus 1, then assign to the j, update the j. So these two, again, is a constant. You will just take the constant time to finish it. The key is this step. I need to run n iteration. Yeah. So as you can see, the problem size is the n. If my n increase, that means I need to run more iteration between line 3 to line 5. Again and again and again, n iteration. So you can expect that the computational times, the time complexity, will affect by the n. Compared to C0, C1, C2, C3, how big it is, it doesn't matter. The n playing the role. My problem size, my time complexity will increase linearly with the n, with my problem size n. Yeah. So this is considered is a linear time complexity. The time complexity increase linearly. That means your n increase, your 10 times, your function also will increase 10 times. On up. Okay, sorry about that. Another, so for loop, we will run the double for loop. Let's say in this example, we have 2 for loop. So what happened? Same thing. Your operation is constant time. Then this summation is constant time. I'm trying to sum all the element in a metric. So internal loop, I run n iteration. Yeah. Then you will take linear. Then external loop will run m iteration. So total, you will run m times n. So the complexity, you will expect that this one will increase quadratically. So compare just now, you only have one loop, you run linearly. When you have two nested loop, it will run quadratically. Yeah, if m equal to n. So your problem size will increase. If let's say n equal to n, internal and external will be quadratic. Your n increase, let's say your n is equal to 10. You can see the problem, let's say n equal to m. If my n equal to m equal to, let's say 10. So how many iteration do I need? Total number of iteration on this particular operation is 100. If my n and m equal to 100, you can expect that you will go to 100 square. Yep. So that is repetition structure. Okay, I think this is simple case. How about this? How many this AJ comparison are evaluated in the given two repetition structure? On your right hand side, the two for loop, I take how many? How many this particular operation are evaluated? N square over 2. Any other answer? I times j. Why I times j? Any other answer? So same thing. Basically, time complexity is trying to no. Any more? Anyone got better answer? Okay. So basically, we trying to count the number of operation. Time complexity is trying to count the number of operation. Yeah, we need to run. Yeah, one guy quite close to it. So you can see that in this example, yeah, I equal to 1, j equal to 0. When I equal to 1, you run the inner loop. So not surprising, j equal to 0, you can execute. Then when j equal to 1, you stop. Because j less than I. When then inner loop finish, then external loop, I will increase by 1. So I equal to 2. So when I equal to 1, I need to run one iteration internally. When I equal to 2, I need to run 0 and 1. So I need to run 2 iterations. When I equal to 3, I need to run, yeah, you can see the pattern, 3 iterations. So that means when I equal to 1, I run 1 iteration. When I equal to 2, I run 2 iterations. When I equal to 3, I run 3 iterations. When I equal to 4, I run 4 iterations. Not surprising. Then I keep doing this until when to stop. When I equal to n minus 1. So then you run n minus 1 iteration. When I equal to n, you will stop. So this is the total number of operation. Maybe I call it Wn. Yeah, the number of operation are evaluated. So what is the answer? This is clearly is an arithmetic series. Yeah, 1 plus 2 plus 3 plus 4. So how many terms? I have n minus 1 term. N minus 1 term. 1 to when I equal to 1. Yeah. So the first term is 1, the last term is n minus 1 divided by 2. So the answer is n times n minus 1 divided by 2. Quite close. But still no one get the correct answer. Okay, so in this function, so the number of operation is actually, you can find that actually is still quadratic. Yeah, it's n squared minus n. Yeah, you can observe that it's n squared minus n divided by 2. So that means when my n increase, actually the number of operation will quadratically increase. And that is quite expensive compared to single loop you see earlier. Yeah. So that is how we analyze the repeatedly structure. Yeah. And not surprising, you can see that analyze this time complexity, a lot of time you need to use the series. Yeah, maybe not only arithmetic, maybe geometric series, depend how the loop change. Yeah, every iteration, how your condition, your increment change. Yeah, then the series will be different. Yeah, that's why, again, I keep saying that you need to revise your mathematics, especially this series part. Yeah, you need to know how to calculate the geometric series, arithmetic series, and all kind of this kind of combination. Yeah, because it's quite easy to, I just need to change my increment, I change my condition, 2 for loop, 3 for loop, and that will affect the series. Every time will be very different. But generally speaking, if you run 2 for loop, not surprising that normally it should be a quadratic function. Another type, of course, you learn any programming language got for loop. Then another one is the if-else statement and switch case. And so if-else statement or switch case, that means it's like you sometime maybe run x in this example. Sometimes you maybe run this portion. Sometimes you maybe run this portion. Sometimes you maybe run this portion. Depend the scenario. So when we analyze the time complexity, when we encounter the if-else statement and switch case, we need to consider it's not just one. It's not that straight compared to the previous one. We need to consider a few scenarios. What is the best case? What is the worst case? And what is the average case? So in this circumsystem, let's set all these primitive operation having the same computational times. So of course, x less than a just need to run one primitive operation. Then x greater or equal to a, that means when this condition is false, they will run this portion, they will run 2. Then let me assume that running this part is cheaper or lesser times. Okay, so my time complexity, let's say, is C1. Then the worst case, I need to run 2. So let's say this is C2. Which is C2, assume that C2 is greater than C1. So C1, C2, that is a so-called the best. We need to identify which circumsystem is give me the best case. This is give me the best case. When x less than a. When x greater or equal to a, I consider this is the worst case. In this simple example, only 2 scenarios. Either you run the x less than a or x not less than a. So that is 2 things in here, but sometimes it may be more than that. Sometimes maybe you have more than 2 combinations. So that is the best case and worst case. Then the third thing you need to consider, and that is the hardest one, is the average case. Average case, that means you need to know all the possible scenario, and each possible scenario and the occur probability you need to consider. like in this scenario, in this simple example, you only have two cases, C1 and C2. Yeah. Either you run this part or run this part. And if you run this part, let's say you have a probability, the chances to run this part is P1. The probability to run this part is P1 minus P. 1 minus, you only have two cases, 1 minus P1. Yeah, then this one cost you, this one you need to take, the cost is C1. Then this one, the cost is C2. Then you just sum it up. Then that is the average case. Or you can think it's an expectation value. Yeah, so it's the same thing. In short, I'm trying to take the average among all the possible case. Yeah, this is the average case. Okay, should be quite simple. When you go to switch case, or when you go to, of course here I give you this a simple scenario. Sometimes you need to first is figure out how many scenarios are there. Yeah, so here got 4 cases. Among 4 cases, let's say I tell you that this is the time complexity of each cases. Maybe the first one compute the summation, they take 5n linearly. Then searching, search the binary search tree, it takes logarithmic times, 6 times log 2n. Then print out, take 3n. Then maybe search the minimum, take another 4 logarithmic to base 2n. Yeah. So among these, which is the best case? Yeah. 1, 2, 3, 4. Case 1, case 2, case 3, case 4. Which one is give you the best case? If I already tell you each of them, the time, the computational times. The first one take 5n. The second one take 6 log 2n. The third one take 3n. The last one take 4 log 2n. Case 3. Okay. Any other answer? Four. Yeah. Okay. Yeah, the answer. Okay. Case 1. Okay, then this is something again I need to give you a revision. If you think about it, if n equal to 10, the first one is 5n, which is, that means they need to, if my problem size is 10, 5n is 50. Yeah, maybe I don't need to plot the graph. Wow. Interesting. So when my n equal to 100, 5n is 500, not surprising. This is a case 1. Okay, now more. Case 4, finally. Everyone realized the problem. Okay, if you use the log 2n, 10 is about 3 point something. Should be 18 plus something. Yeah. Then 100 is about, 100 is how many? Let me do a quick calculation. 6 point something, 6 point something times 6. So this one is 33. Then 3n is 30. When the case 3, 3n is 30. Then this one is about 300. Then the last one is n equal to 10. 10, 4 times 3. So it's about 12 something. Then this one is about 624. So answer is very obvious. Should be case 4. Okay. So the case 4, of course, you may do some, when you do the switch case, starting you maybe do some constant time. That is not important. The key is when my n increase, this part will decide the computational times, will dominate. Yeah. So the worst case should be the linear one. This one, you can see. Every time you give me any m, yeah, this case is always take the longer times. Take most of the primitive operation. You need to do a lot of operation linearly. Yeah, you need to run 5n whatever iteration or whatever. Yeah, but this one logarithmic one, 4 logarithmic is just only 12, 50 and 12, 524 compare. Obviously, this is the best case. This is the worst case. Yeah, so sometimes if you're not sure, you can. What I'm trying to show you is like you're just trying to substitute some number. Better is like trying to substitute n equal to 10, then 100, you increase 10 times, and then see how the number change. Then you can observe that, yeah, which one is better, which one is faster, which one is slower, when you are not sure. Yeah, but generally speaking, you should realize that this is the linear function, this is a logarithmic function. Yeah, if you plot the graph, linear function, when your n increase, the function will increase linearly. But logarithmic, after a while, you'll saturate. Yeah, the growth is not that fast compared to the linear. Quadratic one will grow in this manner. Yeah. So what is the average case? Then I need to know the probability for each cases. Yeah. And then sum it up. For each cases, I need to know this probability. That's why I said the average case is always the hardest part. I need to know the probability for each cases and then multiply with the corresponding time complexity for each cases and then sum it up. Yeah. So that is depend. So sometimes you can make this assumption saying that they have an equally chance. Then the probability, 4 cases, then in each cases the probability is 0.25. Then you can do the summation. But sometimes it may not be true. Yeah, it may not be equally. Yeah. So that is depend on the question itself. So you need to think about it whether you make this assumption they are equally is make sense or not make sense. Yeah. If the problem didn't state, you can make the assumption, but you need to think about it whether, because sometimes the chance, you can observe certain cases maybe obviously they have a higher chance, they are not equally. Yeah. So this thing you need to take notes. Another thing, okay, for an average you need to consider is like one thing is the probability, another thing is how many scenarios are there. I think first thing you need to consider is how many scenarios are there. Of course, here, these 2 examples is very obvious, but in practice, a lot of times, the number of cases may not be so straight. Yeah, and then after that, you list out all the possible case. You need to consider best case, worst case is always the easiest one to figure out. Then average case, you need to consider the probability. Yeah. Then you do the multiplication accordingly, then sum it up. Then that is the time complexity for average case. Okay. So for example, this one, after we combine the while loop and the if-else statement. Yeah, this is what's the typical one you have in your first part, the linked list. Let's say I have a linked list, 1, 2, 3, 4, and then I'm trying to do some searching to search whether the key is equal to A or not. Yeah, given A, whatever. So, and then if equal, then I will terminate my while loop. If it's not equal, I will go to the next linked list, to the next. Here, I will go to the next. And then to check, then next iteration, I will check whether equal to A or not, equal to A or not, equal to A or not, until I reach the last nodes, then I break this while loop. In this circumsystem, of course. So in this circumsystem, the best case is A equal to 1. In my example, that means the search key is the first item in the list. Then you just need to check, compare. Then you don't need to enter the while loop you already found. Then you can break this you can stop the while loop just in, can consider 0 iteration. Yeah, so you got the answer. That is so-called the best case. Worst case, what is the worst case? Probably you search this one, not the case. Search this one, not the A. Search this one, not the A. Maybe search this one, yeah, whether it's A or not. If it's equal to A, then you don't need to enter. If it's not equal to A, you still need to enter one more times, and then you break. Yeah, so either the thing is the last item or the thing is not exist. That probably is the worst case. So in that circumstance, that is the worst case. And you will find that you need to run when A is the last item. Let's say the A is the last item. You need to run this loop n-1 iteration. Yeah, depend the number of items you have, plus just now the first line, C1. Yeah, so that is the worst case. Erase all the... Okay, so I need to run this while loop n-1 times to search this one, this one, this one. Normally you just draw a simple example, you will find that you need to run n-1 times for this inner loop to compare until you find this A equal to 4. Okay, then you stop. So the number of primitive operation you need to run is, you take so much time. So what is the average case? Yeah, best case, worst case. Yeah, best case, first item. Worst case, last item. Yeah, the hardest one, again, as I said, the hardest one is finding the average case. Finding the average case, you need to check first item, and then you check the second item. You check the, yeah, it can be first item, it can be second item, it can be third item, it can be fourth item. So you need to sum all the cases. Yeah, let's say each cases makes sense. Yeah, like I said, the probability reasonable, right? It can be the first item equally. Second item also can be third item. They have an equal chance. So in that, yeah, we can assume that every item in the list have an equal probability as a search key. Yeah, reasonable. This assumption makes sense. So yeah, I need to find out. So the probability for each case is 1 over n. You have n items, each of them have an equal probability. That means the probability is 1 over n. Then it can be need to run C1 one times. Yeah, the best case. The next one is 1 over n C1 then plus C2. Run one time. That means you enter the while loop. Yeah, if it's a second item, then you run the while loop one times, one iteration. Then you run the C1 plus 2 C2, 2 iteration, and so on and so forth. 3 iteration, 4 iteration, to n-1 iteration. So this one, I can rewrite it in this form. 1 over n C1 plus C2i minus 1. I can be from 1 to n. So the first term is 1. The first term is 0. 0 C2, 1 C2, 2 C2. The last one is 1 over n times C1 plus n minus 1 C2. Right? So that is the average case. Of course, not end yet. Need to do the calculation. Yeah, you just do the summation. This one is NC1, then this one C2I minus 1. You do the summation. I minus 1. This one can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, again, this is a arithmetic series. So you sum it up. Okay, how to... So this part is 1 over n times nc1, so you cancel. Then this one is c2 over n. C2 over n, summation of this thing. So this one, the first term is 0. The last term is n minus 1. Divide by 2. Then how many terms are they? N minus 1. I have n term. So n over 2, 0 plus n minus 1. That is the summation of this arithmetic series. So then just simplify this, then you get this. So again, yeah, a lot of time after you get this answer, trying to understand what does this function trying to tell you. This function just trying to tell you that, yeah, this is a function of, it's a linear function. Okay, it's a linear function. So that means your problem size increase, the computational times, the time complexity just linearly increase. So yeah, not surprising lah. This is the linked list search you have learned earlier. Yeah, they do the linearly search. Yeah, but I think intuitive you know that. Yeah, but proper way is through this analysis to showing people that, yeah, you know the best case, worst case, you consider best case, worst case, and the average case. Of course, this is a very simple example. You maybe not appreciate that, yeah, it's a linear, you know that. But sometimes it may not be that easy to figure out which one is the best case, which one is the worst case. In what circumstance you get the worst case, in what circumstance you get the best case. And yeah, how to calculate the average case. Yeah, this one, I would say to some people maybe already can see some people have no idea how to calculate this. I think typical things you need to make sure that you're able to, after you write now just now the C1 plus C2, C1 plus 2C2 and dot, you're able to write now this as in this notation. After that, you know that this particular thing is the arithmetic series. If you're not too sure, you can expand it out to figure out that is the arithmetic series. And then you trying to find out I don't know, some people memorize the formula. Some people can derive the formula on the spot. Yeah, you have to find out the general summation. Yeah, then you will find out that it is a linear function. Yeah, in the end. So that is why I keep saying that you have to revise your mathematics if you really forgot all the formula. Yeah. Well, for this module, we have the final quiz in week 14. So these are the things we will test you during the quiz. The lab test programming, well, it's just coding. So maybe this part, you don't have to worry so much. I won't be able to test you in the coding, the lab test, but I can test you in the quiz. So make sure that you know how to do this calculation. Tutorial, I have, I think, another 2 to 3 questions. Yeah, for let you to analyze some algorithm. Yeah, here again is an introduction. So we didn't set too difficult. I think not too difficult. I hope so. Yeah. Another one. Yeah, just now already repetitive, and the if-else statement, the control statement. Then now the hardest one probably is the recursive one. So recursive function, all these function, all this time complexity analysis, basically we are trying to count the total number of primitive operation in the algorithm. So how to count the total number of primitive operation in a recursive function? We need to figure out each recursive call, we take how many primitive operation first, and then multiply by the number of recursive call. So basically that is the total number. So that's it, I need to know how many primitive operation in each recursive call, and then followed by I need to find out this particular recursive function been recursively called how many times. Then I can find out the total number. Yeah, for example, again, just now the factorial one, I rewrite it into a recursive version. This is the recursive version. Yeah, so each one, that's mean each recursive call, basically I only do, another thing, I think common question people want to ask is like, there are so many operation. Which one I supposed to calculate, or should I including the constant time all the times? Actually, the constant time just now I show you in the past few slides, it just show you that just a kind of a guide only. Later you will find that we don't really bother the computational time difference between different primitive operation. You can assume all of them are the same. So that means the C1, C2, you all can assume they are the same for each primitive operation. Otherwise it's very hard for you to simplify to relative simple. Like this one, C1 and C2, you can assume they are the same. When I derive, I just want to show you that I'm calculate different primitive operation. I don't want to miss out the things. So I call the first line as C1. The operation inside the while loop is C2, is some constant time. Because the difference compared to the n, C1, the difference between C1 and C2 is nothing compared to n. My n increased from 10 to 1 million. Your C1 and C2 may be different, it's just a few microsecond, millisecond, nanosecond today. So multiple by 1 million, my n increased from 10 to 1 million. This C1 and C2 difference is negligible. So you have to, because later you will find that actually what we concern is this is a linear function, or this is a quadratic function, or this is a logarithmic function, or cubic function, or logarithmic function. That is what we concern about in the time complexity analysis. So here, let's say I still consider this operation is C2. This one it takes C1. This one takes C1. This one takes C2. Well, it's about the same. So the key is how many recursive call I have called. Itself will call n So you will factorial n minus 1. You do 1 time, 2 time, 3. n minus 1, n minus 2, n minus 3, n minus 4, 5, 6, 7, 8, 9, 10. Then eventually n will become 5, 4, 3, 2, 1. So total number of recursive call will be n minus 1. Including itself, that means is n call, n function call. And recursive call is n minus 1 recursive call. Excluding itself. So in each in each call, you need to do this multiplication. So you do the multiplication n minus 1 times. Then the last one, you only do C2. So the total cost is C1 times n minus 1 plus C2. Again, you can see that whether C1 and C2 are equal or not, in the end, the time complexity actually is a linear function. It's a linear function. It's a linear function. It's linearly grow. With the problem size n. Another example. This one. So normally, when we have getting more and more complicated function, we may not ask you to analyze the whole function. Sometimes the question you have to read carefully. Here, I just want you to count the number of this particular operation, array 0 equal to A, which is happen at this point and this point. So you need to find in this algorithm each recursive call. If n equal to 1, I do 1. I do this comparison once. When n not equal to 0, and when n not equal to 1, that's when n greater than 1, I will do this one, then go to recursive call. Either run this line or run this line. My n will reduce by 1 recursively. So how many recursive call? Again, same thing, same as the previous one. I will run n-1 recursive call. I will run n-1 recursive call. And then each recursive call will do one comparison. And then the last one will do the same comparison one more times. So total, is n times. So proper, I've said this is quite simple. It's just every time you do 1 times, then you do a recursive call. So this recursive call itself will do another 1 more times. And then your recursive call n-2, and then n-3, n-4, and so on and so forth. Then after the n, when your n equal to 1, you will run this portion. Then you will run 1 times. So that means this is w1 is equal to 1. So total is, not surprising, expected should be n. So total number of array 0 equal to a in this algorithm is n times. I do it n times. Okay. Of course, this is quite simple. What I want to tell you is that this one, the approach I'm doing is called a method of backward substitution. You can see that I start my w, that's in the number of primitive operation. Let's say this is the function. W is the represent the number of array, this primitive operation, the number of this primitive operation. Then this primitive operation, if I want to know the number, I need to, based on this particular recursive call, I do 1 times. And then I need to know the total number of when n equal to n-1. When the input, the problem size is n-1, what is the number of operation? Then plus the current one is 1. So it's a backward. You can see that it's backward substitute. Then you find out. After that, in the end, you get the base case, w1 equal to 1. Then you get the answer. That's so-called the backward substitution. This is one technique. Another technique, is forward. Of course, not surprising. So for example, this case, which you have just learned maybe last week, about pre-order, tree traversal. Then you're trying to do the the number of multiplication operation. The number of multiplication operation is here. So I do, I mean each number I multiple by time. Then I travel the left subtree and I travel the right subtree. So what is the total number of multiplication operation have done in this algorithm? I think intuitive, you know that this tree traversal will travel every nodes. So in the end, is the total number of nodes. But how do we analyze? Let's say you don't know. What you can do is, I know that if the tree is now empty, then seems it's empty. That means there's no chance to enter this if statement. Then the number of multiplication is 0. Then when w equal to 1, I will end. That means only 1 nodes. I will go in once, multiple by 10. Left and right nodes are empty, so it will not do any multiplication. So total will be 1. Then when w equal to 2, that means when you have 2 level, when w equal to 2, in this scenario, let's say this is a complete tree. I assume it's a complete tree. So in this scenario, you do the multiplication once, then left subtree, you already know just now, this case is 1. W1 is 1. W0 is 0. So you can derive it. W2 will be itself is 1. itself you need to do 1 plus 2W1. Yeah, then which is equal to 3. Then soon you will realize there's a pattern. W3 is 1 plus 2W2, which is 2 plus 1 plus 1 plus 1, then which is 7. Okay, so soon you can derive it. Wk minus 1 is equal to 1 plus 2k. So you can see I'm forward from W equal to 0. When my problem side is 0, nothing, empty. Then one level 2, level 3, and then when my 3 have k minus 1, the height is k minus 1, then I need to calculate 1 plus 2 times Wk minus 2. Then which is this? So this is a what series? No one around? One plus 2 plus 4 plus 8 plus to 2 power to k. Geometric series. Yes. So same thing, not surprising, Wk, yeah. So make sure that you still remember what is the geometric series. Let's say you really forgot. Yeah. Then this one is, you have a series is a plus a times r plus a times r squared, and so on and so forth. Yeah, you want to derive it, yeah, just times r, then you get this. Then the first term minus second term. The first term minus the second term, you get a minus a times r. So this is the geometric series formula. So I want to find this. This one is, a is, in this case, my first term is 1. So a equal to 1. My r is, every time I need to times 2. My r is 2. So it's 1 minus 2 power to k over 1 minus 2. So this is 2 power to k minus 1. Correct. So just now is 1, 3, 7. Then the next one will be 15. The next one will be 31. Then 63. Then 1, 2, 7. Yeah, which is 2 power to k minus 1. So this approach is also known as method of forward substitution. Depend. Sometimes backward substitution is easier. Sometimes forward substitution is easier. Case by case. Okay. Yeah. Of course, proper way. This thing. Yeah. Actually, I already skipped one step. You're supposed to use the mathematics induction to prove that. Yeah. When the base case is true, then k minus 1 is true. Yeah. Then wk is true. Yeah. Then this thing is always true. Yeah, then you can derive and find out that the number of multiplication operation in this particular algorithm is 2 power to k minus 1. Yeah, k is the height of the tree. So when the height of the tree increase, the number of operation will increase exponentially. 2 power to k. Yeah. So this one, the computational times is not cheap. Okay. Maybe before end today lecture. Yeah. How many swap operation? You can see that here they are doing a swap operation. Yeah. I just would like to know how many swap operation will be executed in this particular function. Wow. if you have any question, you also can post in the live chat. Quite surprising. Maybe I don't have to use the YouTube next time, since the attendance rate is so low. N over 2. Okay, one thing you need to take notes, I think quite a number of students. Yeah, one thing, yeah, and it's not end or start, it should be considered, okay, can be lah, if you want to set, it's unclear, you try not to use this, because these two are just an index. Maybe you can use n as a representation. So let's say, I guess John is trying to set n over 2. You need to run so many iterations. Is it true? This one, you can see that every loop you're trying to recursive call, your start index will increase by 1. Your end index will decrease by 1. That means you're trying to run, you're trying to swap the first, they're trying to swap the first element with the last element. The second last element swap with the second element, and so on and so forth. Yeah, they keep swapping. So, well, let's say I really don't know how to do this thing. I just trying to use a simple example. If I have maybe 4 elements, I need to do swap one time. I need to do the swap second time. So if n equal to 4, if I got 4, this string size, this array, this string is have 4 elements, 4 alphabet, 4 whatever. You will take swap operation 2 times. So the swap operation is equal to 2 in this circumstance. If I have 5 elements, you will do it 1 times, 2 times. When start and end are equal, they won't operate. They won't execute this swap operation. So when n equal to 5, my number of swap operation is equal to 2 as well. Can observe. So a quick observation. Okay, maybe I can set s equal to n. I'm trying to use the backward substitution. My Sn. So that means each time I need to do 1 operation plus Sn minus 2. Yes, someone got the answer. So I'm trying to use the backward substitution. So when n equal to 2, so I need to do another 1 more, become Sn minus 4. And keep doing this. So it's 1 plus 1 plus 1 plus dot until Sn minus 2i. So I need to know how many swap operation I have done. Then I need to know that s minus 2i equal to 0. So I will be equal to n over 2. Yes, most of the people got this, but you need to consider the thing is it can be odd number and can be even number. So so in the end you can find that actually is the floor function. Because even number you get 2. 5 divided by 2, you get 2.5. Should be 2, but the answer is 2. So you can observe that actually is a floor function. When it's odd number, there's one of them you won't execute the swap. Actually, it depends on this line. If you put equal, then you will become the floor. Okay? So, that is the forward the backward substitution method. So today you just simply use the time complexity analysis. How you analyze the time complexity on the for loop, and how you analyze when there's a if else statement, when there's a switch case. You need to consider three things: the best case, worst case, and average case. Then the hardest part probably is this recursive function. Yeah, of course the example here we give are relatively easier. You can see the tutorial question. There are another 2 or 3. Yeah, okay. So and this thing, very obviously you can see that you need to have some knowledge about how to calculate the series. Yeah, and I can make it very complicated. Not very complicated. I just need to change the for loop condition, change the increment. Yeah, the series will be look a little bit different. Make sure that you know how to handle them. Okay? After recess week, after you finish your lab test, I will cover the asymptotic notation. Yeah, about the order of growth and so on and so forth. Okay? Yeah, that's all today lecture. Any question? Oh, seems not. Maybe from the answer here, I only can set, most of the people understand it. Okay, n equal to today. Flow start n and start. Yeah, because n, just take notes that here n and start is a variable. Yeah, if you n, unless you fix it, so you need to declare, or you need to define that, saying the elements, the problem side is n. Yeah. Okay, so this part I think should be quite easy to you. I hope so. Yeah, because here we just introduce the time complexity. Yeah. But I have to say that when I including those mathematics together, yeah, it can be not that simple as you can, as you see. Especially when you have, in fact, if you carefully see just now this one, this thing is not that simple. That, when you have two recursive function, this still you can visualize it because you know what is a tree. Sometimes if you don't know, when you have two recursive function, you want to analyze it, it may not be that simple. I think one topic I'm not covered in this module is the Fibonacci number. That time complexity will end out. I mentioned in the last lecture. Is the golden ratio, related to golden ratio. The thing may be not that straight. But that one is not covered. Will not be covered in this module, in this level. But I think you will, after you learn the discrete mathematics, in the next level, actually they can cover it. Okay, I hope you all can handle it. If you have any question, you still can email me. Okay? Let me end today's lecture streaming. Okay? Goodbye.